Hi, and welcome to Lecture 6. This is slightly new, a slightly different format. You would not believe the configuration that I've got sitting here in my library at home. Maybe I'll take a webcam picture of what's going on just for your amusement sometime and post that. But I've got different equipment and I'm experimenting to see if this works any better. So you'll have to let me know whether you prefer this or the hand that gets in the way all the time. Anyway, we are talking this time about limits at infinity in particular, and that includes the notion of horizontal asymptotes. This word asymptote is a funny word. It would be good for you to learn how to spell it, just so that people don't laugh at you. I'm certainly not going to be grading you on the spelling, but the word is asymptote, and it refers to some kind of a limit line. You've come across them before from pre-calculus experience, and of course it has to do with this limiting line in some cases, and we talked about them earlier this semester, and we talked about vertical asymptotes. With vertical asymptotes, you've got this, think of a dotted vertical line somewhere at some point, and the function gets very close to it by growing off to infinity, either that way or down from the other side. So that's an example of a vertical asymptote. Of course, it doesn't have to happen that way. It could happen, where you've got the vertical asymptote here and the function just goes off to infinity that way, and maybe it comes off to infinity that way as well. So you've got vertical asymptote where the limit goes to plus infinity. And we know how to test for these things now. The important thing about a vertical asymptote is that the limit, as x approaches the value a where the asymptote occurs, whether it's there or there, the limit as x approaches a of your function has to be plus or minus infinity. So in this case it would be plus infinity right here, and if you had an example like this one, your asymptote might come down like this, your function might come down like this, and then your limit as x approaches a would be minus infinity. So we've already talked about that. That's not the issue of what we call limits at infinity. There we're talking about what would it mean to have a horizontal asymptote, and you might guess that that's going to have something to do with a limit as x gets large, either going to plus infinity or a limit as x goes to minus infinity. And in fact, that is exactly what we have to talk about. So let me give you another picture that shows this. So here, if you have the x and y axis, and you have some function that, actually one that we know very, very well, it's the function e to the x. And I've often said that this particular function, as x gets small, as x goes this way, e to the x is going to 0 in that direction. And now what we want to be able to say is something that shouldn't surprise anybody. The limit as x approaches minus infinity of e to the x should be 0. Another example, if we had the function 1 over x, which looks like this, it shouldn't surprise anybody that if we talk about the limit as x goes to plus infinity of 1 over x, the answer is going to be 0. So this is the kind of thing that we want to be able to say, and the first thing I want to talk about is exactly what does that mean. And this is going to lead us again to another epsilon type of definition, which will be a little bit painful, but honestly, this is the definition that I understood first. Rather than the one that we did before with epsilon and delta, this definition made much more sense to me when I was a young student, and it sort of led me to understanding limits. So let's see what this has to say. So the question is this: what does it mean when we say the limit as x approaches infinity of f of x equals L? And see, this is different because we're talking about infinity here, which is not a number. So this requires a definition. What does this mean? Okay, so here is the definition. This means, and we're going to start off the same way as we did before, for all, or for every epsilon bigger than 0, no matter how small. So epsilon again is a tolerance. How much error are you going to allow? This time we're going to say that for every epsilon there is a corresponding, there exists a number. In this case we don't use delta, and you'll see why in a minute, but I'm going to call it capital N. And this number, capital N, is what I think of as the point of no return. This is the point beyond which the function has to behave itself. And I'll tell you what that means. For every epsilon, for every tolerance, there is a capital N such that beyond capital N, that means for all x bigger than or even equal to capital N. It's convenient to allow equal because sometimes we need to get hold of that number n just for technical reasons. But anyway, beyond capital N, well, the punchline is the same as what you've seen before. The distance between f of x and L is less than epsilon. So here's what's going on. You've got this function that we think is going to be asymptotic to something. So here's our alleged asymptote. And now I'm going to say that this is L. In other words, the y value here is L. And what I'm saying is that the limit as x goes to infinity of this function, f of x, is supposed to be L. And what should that mean? If this is the function f, as x gets large, f of x is getting closer and closer to L. What does that mean? Well, here's the definition. For every tolerance epsilon. So you remember how we played this game before. We went L plus epsilon and L minus epsilon, and we built the epsilon strip around L. And so all I'm saying now is that for every tolerance, for any amount of tolerance, distance between these two guys, however close I make this, there is a point of no return, which we'll call capital N. In this case, capital N would be about here. There's a capital N such that for any x beyond capital N, the function stays within the tolerance strip forever and ever. Now, of course, the boss is allowed to tighten up the epsilon, make this strip smaller. Fine, in that case, we just move our n to the right, and the function would have to behave itself. So the epsilon n game, just like the epsilon delta game, is the boss gets to pick the tolerance, but then we get to find the point of no return, capital N. And once we've identified that point of no return, we have to demonstrate that beyond that point of no return, every x value is within tolerance of L. And that is the definition of the limit for infinite values, that is, for x getting large. And there's a slightly different definition if you say x goes to minus infinity. The only change there is that x, instead of being bigger than or equal to n, becomes less than or equal to n. And that's all. Okay, at this point we could play the epsilon n game like we played the epsilon delta game in a lab situation, coming up with an n for a given epsilon, but we're not going to do that. Instead, the exercises that you're going to find at this point are all algebraic types of exercises, unfortunately. They are going to require you to have tremendous algebra skills in order to calculate the limits. So what we're going to be doing now is looking at tricks for doing these problems. So actually, I think that's what I want to call this part, tricks. Not shortcuts, but tricks. And the thing is that these tricks you will find useful in later later this semester. So we'll look at a bunch of examples, but before we do that, before we even start talking about the tricks, you need to know a few obvious answers. So, for example, what is the limit as x approaches infinity of 1 over x? Well, that one is pretty easy. That's 0. And you got to think about this the way we've always thought about it. What happens as x gets large? That's what this means. What happens as x gets large? And so the denominator is getting big, the numerator is not doing anything about it, and so the fraction is going to go to 0. It's going to get small. So that's what this statement says. As x gets large, 1 over x gets arbitrarily close to 0. How close? Within epsilon, no matter what epsilon it is, and we can get that close by going far enough beyond some capital N. The same thing could be said for functions like 1 over x squared, 1 over x cubed, or even going slightly smaller, 1 over the square root of x. If you take x and make it get bigger, the square root of x will get bigger also, but it will get bigger not quite as fast as these other guys, but it will get big enough to make this entire fraction go to 0 as x gets large. So yeah, the limit as x goes to infinity of 1 over the square root of x also is 0. In fact, one of the slowest ones around would be, what's the limit of 1 over the natural log of x as x gets large? Well, believe it or not, this takes its time, but it's 0 also. It's that x has to get really, really, really big in order to make 1 over natural log get small enough. But remember, the graph of the log looks like this. So log does get bigger, it just takes its time about it. And so eventually 1 over natural log of x is going to be 0. Or get close to 0 is what I'm saying. This 1 over x squared is a special case of 1 over x to the p, where p is a positive number. And any of these guys are going to go to 0, just like these other ones did, as x gets large. And we already looked at this e to the x, but I want to look at e to the minus x. So as x gets large, minus x is going to go negative large, but e to that power is going to go to 0, so yes, the limit as x goes to infinity of e to the minus x is 0. Now, there's a mirror image of this problem, which is pretty obvious. The limit as x goes to minus infinity of e to the x. So I've negated both of these guys in some sense. So instead of looking at e to the minus x, we look at e to the x, which is this guy again. E to the minus x would just be the flip, right, of e to the x. So if you're looking at e to the minus x and going to infinity, you're coming down this way to 0. Looking at e to the x, as x goes to negative infinity, you're going off this way, and the limit is 0. Okay, so all of these are kind of obvious limits, and the reciprocals of all of these too. And, you know, for example, what happens, these are all kind of dumb questions. What happens to the square root of x as x goes to infinity? Well, the graph of the square root of x looks like this. Starts at 0 and just grows. It's half of a parabola. And so it's no surprise that the square root of x goes to infinity as x gets large. It just doesn't go very fast to infinity, but it gets bigger and bigger and bigger. Okay, so the limit as x goes to infinity of that would be plus infinity, or you could say it does not exist. That would be fine. All right, so now let's look at the first of our real tricks. There are a couple. So we'll get a brand new page for this. The first of the tricks comes up when we try to divide two polynomials, and it works in other cases as well. So I'll give you this by example. The example is the one that you'll find in the book, so you can look at their explanation, look at my explanation, and see which one makes more sense for you. Suppose that you have this fraction, and you're asking what is the limit of this as x gets large. And you see the problem. The problem is that as x gets large, this x squared term dominates in the numerator. I mean, that minus x isn't going to do much to subtract off. So as x gets large, this numerator is going to get large. And then so is the denominator. And so the question is, what's going on here? If the numerator is getting large, that wants to take the fraction to infinity. If the denominator is getting large, that wants to drag the fraction to 0. Who's going to win? The answer is, it's difficult to say. So we need a trick, and this first trick is multiply top and bottom by the same thing, and the same thing in this case is 1 over x to the highest power that you see. So in this case, the highest power that you see is 2. So what I'm going to do is take and multiply this 3x squared minus x minus 2 divided by 5x squared plus 4x plus 1, and multiply top and bottom by 1 over x squared, because that is the highest power of x that I see. 1 over x to the highest power. Now that's a strange thing to multiply by, but you can't deny that that's equal to 1. So I'm not changing the problem. So let's multiply this out. Remember that you're going to have to distribute that 1 over x squared across this entire polynomial. So you're going to get 1 over x squared times 3x squared. Well, that's going to cancel it off completely, leaving you with just 3. And then 1 over x squared times minus x, that's going to leave you with minus 1 over, one of the x's will cancel, leaving you with just x here. Work that out for yourself if you don't see it instantly. And then the last one is pretty easy. That's minus 2 over x squared. This is kind of a pattern that you'll see happening a lot. And the same thing's got to happen in the denominator. Multiply through by 1 over x squared. So 1 over x squared times 5x squared, that's just going to give you the 5. The x squareds are going to cancel. Then you have plus 1 over x squared times 4x leaves you with 4 over x. And 1 over x squared times 1, well, that's easy. 1 over x squared. Well, now we've made the fraction look much, much uglier than it was to begin with. I mean, this doesn't look too bad. This looks pretty ugly. But there's one very, very nice thing about it, and that is I can tell you what's happening as x gets large. Nothing happens to 3, obviously. 3 stays 3. But as x gets large, this guy we've seen before. 1 over x is going to go to 0. Because as x gets large, 1 over x becomes diminishingly small. And the same thing happens with this. So anytime you've got this x or x squared or stuff in the denominator like that, all of that stuff just goes away. 4 over x, it's out of here. 1 over x squared, it's out of here. They both go to 0. So the only thing left standing, the limit of all of that, is going to be nothing more than 3/5. And that's the answer. Now this is a trick. The trick is multiply the top and the bottom by 1 over x to the highest power. Now some of you are looking at this and saying, well, there's another shortcut. The shortcut is, the answer is the coefficient of the highest power of x divided by the coefficient of the highest power of x. And yeah, that's true. But what that does not do for you is it does not give you any reason why that's the way it is. Why should that be the right answer? And what I've done is to show you what you have to do to see that that's the right answer. And the trick that I'm talking about, this trick of multiplying by the same thing, the top and bottom, by 1 over the highest, is a trick that's going to come back again and again. And you'll use it in lots of different circumstances where you may not even anticipate that you wanted to use it. So that's one that I would like you to pay particular attention to. There's lots of problems where this is the trick. In fact, there's some where you wouldn't even expect it. Look at this problem, for instance. Square root of 2x squared plus 1 over 3x minus 5. Same thing. Multiply by 1 over the highest power of x. The question is, what's the limit as x goes to infinity? Well, you can multiply by 1 over the highest power of x, but you see the problem, we've got this nasty radical here, this square root. So, I'm still going to do it, but I need to put the 1 over x squared. See, if I put 1 over x squared there, I can't bring that under the radical as it is. So what I have to do is put a square root of 1 over x squared there. Of course, if I do that, I've got to do the square root of 1 over x squared here, and that's legal. So now this is going to give us the limit of what as x goes to infinity. It's still going to be a fraction. But on the top, now this square root of something times the square root of something else can be written as a square root of one thing. And this 1 over x squared can now distribute across the 2x squared plus 1. So that's going to leave us with 2 plus 1 over x squared. That's not too difficult. Now down below, we just remember, or just notice, that this square root of 1 over x squared is nothing more than 1 over x. So I don't have to have a radical here if I don't want it. I wanted it upstairs because I needed to combine it with that radical. But in the denominator, I don't have a radical here, so I just remember that the square root of 1 over x squared is really 1 over x. And so I multiply 1 over x times 3x minus 5, and I get 3, the x's cancel, minus 5 over x. And as x gets large, this guy goes away, we've seen that, and 5 over x goes to 0. So that limit becomes the square root of 2 over 3. Final answer. Okay? Now, there's a nasty, nasty, nasty question that also comes up here. And it involves a different trick. What happens if x goes to negative infinity? You might think there's not much of a change, and there isn't, except for one subtle thing. When x goes to negative infinity, what can you say about x? Well, x will be negative, in a word. And what do you know about the absolute, no, not absolute value, excuse me. What do you know about the square root of anything? I don't care what you put down here. When you write this symbol, you are automatically meaning the positive value. So this guy, this square root of anything, I don't care what it is always to be interpreted as the positive square root. If you meant to talk about the negative square root, then you've got to stick a minus in front of the radical to talk about the negative one that's the square root. Okay, so what's the point? As x goes to negative infinity now, x is a negative number. So if we're talking about 1 over x, what's 1 over x? 1 over x would have to be negative as well. So could that possibly be equal to this square root of 1 over x squared? No. So in fact, when you go to multiply top and bottom by the square root of 1 over x squared, that's certainly legal. You're allowed to multiply top and bottom by the same thing anytime you want. It's just that when you go to change the square root of 1 over x squared to 1 over x, that doesn't work anymore. It's now minus 1 over x. So, the same problem if x goes to negative infinity, instead of getting the 1 over x from before, we would now have minus 1 over x in the denominator. And this answer here will change only when you get minus 1 over x. This minus 1 over x will have to be multiplied by 3x, and it'll have to be multiplied by minus 5. So that's going to leave you with minus 3 over x plus 5 over x. And the nice thing here is x goes to, as x gets large, 5 over x goes away, but you're left with, I'm sorry, not 3 over x, minus 3. The x's cancel. So as x gets large, 5 over x goes to 0, minus 3, nothing happens, and so the limit there will just be the square root of 2 over minus 3, or minus square root of 2 over 3. So what this is telling you is that as x goes to plus infinity, this is your limit, square root of 2 over 3. And as x goes to minus infinity, it's minus square root of 2 over 3. So in fact, here is the situation. Here's your x-axis, and you've got a limit line here at square root of 2 over 3, and another limit line at minus square root of 2 over 3. So you've got these horizontal asymptotes. And as x gets large, the limit is approaching here, and as x gets small, the limit is approaching here. Now, I don't really know that this is how the graph looks, but I can tell you that the limit is going to approach that line. All right? So that's what horizontal asymptotes are. Anyway, if we look back at where we started here, this was the trick of multiplying top and bottom by 1 over the highest power of x. Okay, second trick, and really there aren't too many more. The second trick is to deal with differences where your difference is going to end up being like this, infinity minus infinity. What's going on when you have something like that? If the first term is getting big, you expect the answer to get big. But wait, what if the second term is also getting big? Then it's not clear at all. And so you've got this tug of war going, and that's bad news. We're going to look at situations where you've got infinity minus infinity with radical expressions, square roots. And the trick here is to multiply by 1 in a very clever way. You multiply by basically the first guy that's getting large plus the second guy over the first guy. I'll call this infinity 1 and infinity 2. Infinity 1 plus infinity 2. So you multiply this difference by what we call the conjugate. But you have to do it as 1 so that you don't change the problem. Okay, here's the example. We want the limit as x gets large of the square root of x squared plus 1 minus x. Okay? Reality check. What's going on as x gets large? As x gets large, obviously that gets large, plus 1 gets large, square root of the whole thing gets large. So yeah, this whole first term goes to infinity. But then so does the second term, and you are exactly at this infinity minus infinity. You can't tell just by looking what's going on here. The answer could be 0, it could blow up, it could go to negative infinity, it could go to 17. Anything can happen. You cannot just assume the answer is 0 because you're subtracting infinity minus infinity and that's 0. No, that's wrong. Now, as it turns out, in this case I think the answer is 0, but I don't really remember. I have to work it out. It could have been something else. It just depends on what these numbers happen to be. Anyway, the trick is multiply top and bottom by the conjugate, which would be the same thing with a plus in between. And you have to multiply by 1 so that you don't change the problem. Okay? This quantity is 1 that I'm multiplying by. So when you multiply this, the nice thing about it is what's going on? You are doing an instance of a minus b times a plus b. And when you do that, a minus b times a plus b is the difference of two squares, a squared minus b squared. And the nice thing there is it makes the square root go away. So when you multiply that mess out, here's what happens. You get the radical going away, and you get x squared plus 1 as your first term. That's your a squared, and then minus x times x. That's all you get in the numerator. And then in the denominator, it's still square root of x squared plus 1 plus x. That does not change. So you keep this guy. So this is your fraction, and obviously you can simplify. So you get the limit as x goes to infinity of the x squareds cancel, leaving you with just 1. And downstairs you have x squared plus x, x squared plus 1 plus x. And then your numerator does nothing as x gets large. It stays 1. But the denominator is getting bigger and bigger and bigger, so yes, the limit here is 0. Okay? So this is the trick that will be used anytime you've got a difference of two quantities, both of which are getting large. You're going to need to multiply by the conjugate to make that work. Okay, one last thing, and this is an example I don't even need a new page for. This happens to be my favorite function, and that is the inverse tangent. Also known as arctangent. So arctangent of x has a graph that looks like this. Now, I don't expect you to know this just now, but I will expect you to know it because this is a very, very important function. It has two horizontal asymptotes. And the graph of it is a flip of the tangent function. So it goes just like this. And the nice thing about this function is that it spends its life between pi over 2 and minus pi over 2. Alright? So you can answer the question, what is the limit as x goes to infinity of the inverse tangent? That's pretty obvious. As x goes to infinity, x gets larger and larger, the y values are getting closer and closer to pi over 2. You just have to know that. And what happens on the other end as x approaches negative infinity for the inverse tangent? Well, obviously, as x gets smaller and smaller, the y values are going towards this number, minus pi over 2. All right? So just remember that example because it comes up a lot. It's a very, very nice example. Inverse tangent may not be your best friend. I can't say that it is as important as e to the x, but it's a nice function in a lot of ways. It does some nice things for you. And it's a good example here of a situation where you've got two different horizontal asymptotes, and you've got a function that is really, really continuous. There are no holes, no jumps, no problems with it at all. It has a limit everywhere. The limit agrees with the function, and there are no vertical asymptotes, no places where you have undefined or discontinuous or anything, and you have two finite numbers as horizontal asymptotes. Right? That is it for today. Let me know if you think this is better or worse. Bye.